Thank you to all the organizers for having me here today. Let's see, I got to start up the other. So I am giving a PowerPoint presentation, Frank. My apologies.
I never say anything against that. I said, why don't you give good talks?
Okay. You can let me know at the end if I satisfied that. So before I get to talking about the content, I just want to acknowledge that there's a lot of collaborators that have participated in this work with me. The main ones are Andrew Samazi at Notre Dame. We've been working together since the late 80s. And then John Hallenstein and Dan Bates. This includes the Bertini software development, which you may have heard of. I'll mention it a little today. And a more recent thing is laser just died. More recent thing is Bertini Real software, which includes these guys, plus also Daniel Brake and Winrui Howe. Dan's here. And we'll talk about Bertini Real more at the end of today. And then I'll speak a little bit about a couple application areas. And the mechanism design work is with some mechanical engineers at University of Dayton. And sphere packing work is with Miranda Holmes-Sirfon at NYU. Oh. Well, there might be too many things to handle. Thank you, though. Okay, quick outline. Start with a little motivation, then I'll give a brief background in numerical algebraic geometry. A lot of people here have had some exposure to it already. Some more recent work on intersection of algebraic sets and just a little bit about what we're doing with real algebraic sets. I'm going to let Daniel talk mostly about that today. And then these application areas. So motivation, my motivation for getting into algebraic geometry is kinematics and robotics. And here's an example of some of the work I've participated in. This is Robonaut 2. It's an anthropomorphic robot with 42 degrees of freedom. It's up on the International Space Station. It's been up there 3 years now. So this was a fun project to be involved in. You can see how he's situated in the space station with what we call the task board here, a bunch of switches and cables to connect and things to experiment to see what a dexterous robot can do. In August, NASA sent up a leg module. So this, what we built was from the waist up, and they've now sent up legs, which is a nice thing you can do with a robot you can't do with an astronaut, send his legs up later. And so sometime, I think it'll probably take till next year till they, you send things up when you can and then you get them out and use them when they're on the schedule. So sometime next year he'll be wandering around the space station. So that's kind of cool. But let's look inside of Robonaut a little bit. This is it's a CAD drawing of the forearm and hand. The hand has 12 degrees of freedom, and you have to actuate those. You can't put all these motors in the hand itself, so just like you and I, the motors are back here in the forearm, and tendons go out to the fingers and actuate them. Tendons can only pull, they can't push. You can't push a rope, as the saying goes. So you have to actually have more tendons than degrees of freedom out here. So with 12 degrees of freedom, I believe there's 16 different tendons coming out. They all have to pass through this wrist. So you want to keep the wrist open. And here is an actual photograph with the covers taken off of the Robonaut wrist. This is the hand, the gold part. This is the forearm is over here. And you can see all of these tendons and their conduits going through the opening. So we needed this wrist with an open structure. It has a pitch axis, goes like this. A yaw axis goes like this. And then it has these, what I call push-pull links on the outside. And it makes a closed chain mechanism that you can now move with 2 degrees of freedom and have it all open for the tendons to come through. So where's the polynomials in this? Well, I've got a motor that drives this little ball forward and backwards, another one up here. And then I want to know the relationship between the translations here and the rotations here. So you form up a system of equations. If you write it in the sines and cosines of the angles, it's all polynomial. You put in sine squared plus cosine squared equals 1. You're good. It's a polynomial system. And then you can look at it two ways. One is if you put in the slider values you'd like to solve for the angles, that's the forward problem. The inverse problem is you put in the outputs, the angles, and you want to solve for the slider values. And so depending on which way you go, you have either 4 solutions or 8 solutions. That's not by far one of the, it's one of the simpler problems that we've solved in the kinematics arena, but just thought it's a fun one to show because you got the photograph there and it's on Robonaut itself. Here's a picture, a diagram that shows from a bigger picture perspective what you can face in kinematics. So in the center here I have what I call the mechanism space. And if I have a system, I'll call it f of x and p. So this would be like all the joint angles and the output space coordinates. And then this would be the parameters, the mechanism. So if we go back here, what are the parameters? It would be where is this sliding line in the coordinate frame of the forearm? Where is the other one? So the physical dimensions of the device that you built. But I can characterize all devices of this type that have 2 sliders, 2 push-pull links, and so on, and in one system, and parameterized by those geometric things. So now if I look at V of f, that's what I mean by M in the middle of this diagram. So it encodes the whole family of, let's say, Robonaut wrist types, okay? So now I have just a simple projection to pull out the design parameters, just pull out P, but I also have these polynomial maps to the outputs and to the inputs, and we'd like to move around in this commutative diagram. So when I talk about forward kinematics, it means you start down here with a device of a certain design, so I know the parameters, and I'm giving you the inputs. I'd like to tell you to tell me what my output is. Or there's kind of a symmetric problem is I give you also the design, but now I'm telling you what output I want from it. Tell me what input. So how far should I turn the motors that drive the links to get the output that you want? But then there's other problems. One is you start with the design parameters and you ask what's the whole set of outputs I might get. That's called workspace analysis. I'm not worrying about what input it takes to get to them. I just want to know the whole space. And then some of the hardest problems go this way. And I'm actually faking this a little bit. You want to start with the outputs you want to achieve and arrive at the design parameters of a mechanism that will give you those outputs, or that output space. And the reason I say I'm cheating a little bit is typically I have to give multiple sets of outputs that I'm trying to get. So it's really a cross product of a bunch of these that go that way. So it's not just a map from output to parameters. And I'm going to talk a little bit about one of these problems. Those tend to be hard because when you start taking cross products of this, things get big. So another motivation is sphere packings.
Is it cross products because of the extra joints? Is that?
No, what it is if, and I'll get to this later. Suppose, let's take a simple mechanism. This is called a 4-bar linkage. This means these points are fixed in space, but these are rotational joints. And when you turn a joint here. This point up here will make some curve. Turns out it's a 6th degree curve. And what I might say is, I'd like you to design a 4-bar that can go through can interpolate certain points. So the cross product comes up from saying, the solution to the system has to go through this point, and now it has to go through this one. So there's a copy of the system for each point you want to go through. Now, this is another problem area I've been working on a little, called sphere packing. And the question is, how do microspheres cluster? This is work came out of Harvard. Vinny Manoharan is a physicist. Mike Brenner is a mathematician. Arcus did her PhD on this in 2011. And Vinny is actually doing the experiments. He has these micro wells with I don't know if it's water or some other fluid. He puts the microbeads in. He lets them cluster. He takes X-ray images of them and then figures out how they actually cluster together. So that's like the experimental side. The math side is to try to predict how they'll cluster together. So when these spheres come in contact, they have a surface adhesion. They'll stick to each other, and they'll keep moving. If there's any degrees of freedom, they'll tend to move until they make another contact, and eventually you end up with a rigid cluster. So the question is, what are the rigid clusters that you can make? So if you have 6 spheres, you'll make essentially an octagon, where each sphere is at the center of one of the vertices. The centers of the spheres are at the vertices of an octagon. As you move up, you get more and more possibilities. It starts to explode. And this is just what they call the table of new seeds. These are the ones that are not, that you can't get just by putting like tetrahedra together. Okay? I'll explain that a little bit more. But the point is, each sphere-to-sphere contact is a distance constraint. And so this project of predicting all the different ways they can cluster comes down to enumerating the possible adjacency graphs. How can which spheres contact which other spheres? And then for each of these, there's a system of quadric polynomials to solve, because it's a distance constraint, and that's a quadric. All right, so that's a little motivation. Let's get into numerical algebraic geometry. So some people have seen a lot of this before. Other people, I'm assuming there's some people that haven't seen it before, so I'm going to give you a quick ramp up into numerical algebraic geometry. So let's say I want to find all the isolated solutions to a polynomial system f that's a map from Cn to Cn. So the same number of equations as unknowns. And what's the approach? We're going to cast f of x as a member of some parameterized family of systems. So this looks like what I drew for the robot. These kind of things arrive naturally, but this process is usually making up a family that's convenient at our convenience, where one member of the family is the system we want to solve. So here, my parameter space, it looks like maybe it's just a 1 parameter space, the real and the imaginary part of the 1 parameter. And for one value, here is the system I want to solve. Now I'm going to solve this for a generic member of the family. So it's some other P1. I'm going to solve it, and I'm going to have some set of isolated solutions I'll call S. Somewhere in this parameter space, I don't know where, but probably there's exceptional points where the number of, if this is a generic number, its number of solutions is the same almost everywhere in the parameter space, but there'll be places where the number of isolated solutions can fall. You hit singularities and so on. So there's some non-generic parameter points. So the game is to find a general path that avoids the non-generic points And then you just track a homotopy. Just put that path in here. You move through parameter space. You track the solution sets from the S solutions that you know at P1 to the solutions at P0. And that's what continuation is. Everything we do comes down to some kind of game of this form. So, a few things to note. First of all, the non-generic set, its complex codimension 1, so its real codimension is 2. That means that a randomized path is general for t in 0 to 1 with probability 1. So I don't know where the non-generic points are, but if I just randomize the path I take, the probability of hitting them is 0. And that's what we depend on with probability 1 algorithm. So the key to this whole thing is how do I pick this family that has a generic P1 that I can solve at easily enough, and also I would prefer to have the number of solutions in this family as small as possible. It'd be great if it had the same number of solutions as my target. It might have more. Okay, so finding a family it seems like solving here would be just as hard as solving here. How does this thing get off the ground? Well, the easiest way to show that is the original homotopy that satisfies these conditions. This is what we call the total degree homotopy. It's sort of the simplest way to go, and it's been around since, I think, Garcia and Zangwill did it in 1977, if I remember right. So what do? You take, for each polynomial in the target system, it has some degree. You match it with a monic polynomial in just one variable with that same degree, and you just line all those up. Well, what's the solution to this start system? It's just the roots of unity in each one of these, all possible combinations. So you have the product of the degrees, number of solutions here. And by Bezout's theorem, that's the maximum possible. So this is a generic problem in the family. And so now I just have to connect it up to the target with a general path. And it's easy to show that if you just do what we call a linear homotopy, 1 minus t here and gamma t here, where gamma is random complex, that this is a probability 1 algorithm. In other words, that just putting this one random complex number here is enough to ensure that you have a 0 probability of hitting the non-generic points. So let's up our game a little bit. Problem 2. Now I have a polynomial system with the number of equations and unknowns not necessarily equal, and I'd like to find the whole v of f, all the points in Cn that satisfy that. Well, what does that mean when the dimension is bigger than 0? I mean, we're working on a computer. I can't list, it's on the complexes, I can't list out all the solutions. What does it mean to give you the solution set? Well, instead of, if it's isolated points is all you want, I can list approximations to all the isolated points. But for a higher dimensional thing, what I'm going to give you instead is what we call a witness set. So in fact, what we'd like to do is have one witness set for each of the irreducible components of the variety. By setting this as our goal, we can reduce problem 2 to several instances of problem 1. So we're just looking for isolated points that satisfy the conditions of the witness set. So what is a witness set? It's a triple. So an algebraic set A, a witness set for it consists of 3 things. F is a polynomial system such that A is an irreducible component of V of F. So in a lot of times we start with F, but later we oftentimes have a derived F that came from some other source in the beginning. So we need that. We need L is a generic linear space of complementary dimension to A. And then the third element is what we call the witness point set. It's the intersections of L with A. So if A is degree D, we're going to get D points in L intersect A. because L is a generic linear space. How do you get a generic linear space? You take linear equations and you pick the coefficients with a random number generator. And again, with probability 1, that's going to be generic. So that's my introduction to numerical algebraic geometry. What do we got in this Bertini package? We've got path tracking that has adaptive precision. So when you deal with high degree systems, you can get ill conditioning. We expand the digits to make sure that we are still computing meaningful things. And singular endgames, if we head to a singularity, if your target is not generic, some of the paths will become singular at the end, but you know where it's happening, so you can take a special procedure to solve for the singular endpoints. If we can do various versions of zero-dimensional solving. We can do positive dimensional sets and the irreducible decomposition, which means producing a witness set for each irreducible component of the variety. We can do things like membership tests and intersection, and I'm going to talk a little bit more about intersection. So this is the Bertini package. We first released it in 2008, so it's been around a little while now. It's now open source, and we continue to update it. So I encourage you to look it up and give it a try. And if you want more background than what I just gave you, there's a couple books now. And let's talk about intersections. Now, this is the first dense slide in here. But let's pick it apart a little bit. So suppose I want to compute A intersect B. Well, I'm in this world of numerical algebraic geometry, so how do I even give you A and B? I'm going to give you a witness set for each. So I've got a system of polynomials, a linear space, and a set of witness points. Okay? And I have one of those for A and one of those for B. One way you might try to compute A intersect B is just to take FA and FB, stack them up together, and solve for the irreducible components. That seems good, but it doesn't always suffice. And here's the easy counterexample. Suppose A and B are two components in the same system. In other words, FA and FB are the same. So if you did the irreducible components of this, you would get A out as a component, you'd get B out as a component. You wouldn't get their intersection. It's not an irreducible component in there. So what can you do? I'll tell you what you can do in a second, but I also want to point out that even when this suffices, so that the thing you're looking for is an irreducible component of the stacked system, that going at it that way could be very wasteful. Because suppose V of F of A has many irreducible components besides A. If I just stack these up and do the irreducible decomposition, I'll get the intersection of all those different components with B, and I'm only looking for one of them. Okay? So you don't want to go at it that way. So, how can we target A intersect B directly? And the key maneuver is if A and B are both living in, say, Cn, instead of working in Cn, I'm going to work in C2n, Cn cross Cn. In there, I have A cross B, and then I'm going to intersect that with what we call the diagonal. If x is in A, y is in B, and I solve x minus y equals 0, then I'll have the intersection. So this is now 10 years ago that we first put this forward. The interesting thing is, and something we didn't fully appreciate back then, is that all this gives you is witness points. And if you have a case where stacking A and B together doesn't suffice, I don't have a witness set yet because I don't have a system that this intersection is an irreducible component of. And I've got to construct that now. So how can we do that? So we have this thing that we call isosingular deflation that I don't want to go into the details, but it can start from the witness set and get up. You can start from the witness points and get me a witness set by constructing a system where the intersection is an irreducible component. And the basic idea is this. If the witness points are generic, which they are with probability 1, then the Jacobian matrix JF of A, JF of B evaluated at a witness point has the generic rank, the same rank as almost all points on the set. So I can append the algebraic condition that this is the rank of the set I'm looking for to the original equations. Now I have a new set of equations. That's the old ones plus this rank condition. And then you iterate on that. If that new system isn't, you can test, does it suffice? If it doesn't, you take the rank again and you go again. All right? This is what we call isosingular deflation. Applying this rank condition is a little different than the deflation method that it's built on top of, the one that from Lycan, Verskeldy, there's an E there, and Zhao. That was the first deflation shown to terminate, and it's useful in a lot of areas. But to get what we need here, we had to do this variant on it that will work in this context, and we call it isosingular deflation, because we're looking essentially for the points that all have the same kind of singularity. That's why we call it isosingular. Now, how do we compute all these things? So regeneration is something that will allow us to compute A intersect V of F for some new F without first decomposing V of F. And this is something we've had out for just a few years. I'll give you a little view of that. So suppose we're back to solving a system F1 through Fn. And suppose at some stage we've gotten all the isolated points, that's what I mean by V sub 0, all the isolated points of F1 through Fk minus 1 intersected with some generic linears. Okay? And what I want to go to in the basic step of regeneration is replacing this linear with the next function in the system. And it's fairly simple to do this. We can do a continuation where we move the coefficients of this linear to other values. So we can produce the intersection with any number of different general linear equations. If we do that dk times, where that's the degree of the next function, then we can take the union of all these solution points, and that'll be the solution to this system. Now I've managed to replace a single linear with something that is degree dk, and then I just do a linear homotopy to the new f. That's the process we call regeneration. It's pretty simple idea. And then if you want to solve the whole system, you just repeat that. The interesting thing about regeneration is that if this subset of systems has any kind of special character, things going off to infinity, going into singularities and so on, and you're not interested in singularities, you get to throw all that away, and it simplifies the process as you go forward, as opposed to something like the total degree that shoots for the whole thing at once.
Do you also get to exploit the last few linears to have a dimension reduction? I mean, the last few linear conditions, they define as smaller dimensional space.
Yes. Oh, yeah.
You exploit that as well.
Yes. So there's a kind of a trade-off between moving the coordinates in that subspace versus having reduced the subspace. So we do a little analysis. Sometimes we move to coordinates on the subspace. Sometimes we keep the original coordinates. And you can do a calculation which has fewer operations.
It seems that potentially this allows you to investigate things of low codimension very efficiently.
Yes.
Without having to worry about the full dimension.
Yes. So we have all these pieces around. I've described some of them to you. So let's look at a variant of the problem. Suppose we have A and B witness sets for them, and we bring in a new system F. So this is the kind of thing we have In the old days, we used to just start with a system and we're interested in its solution set. But in this newer world, we want to look at this, look at that, now look at their intersections, bring in new things. That gives you a lot more flexibility about how you can get to the final thing that you're interested in. Okay, so suppose I have sets A and B around, and I want to throw in a new system and compute this intersection. So what we're going to do is a generalization of the diagonal homotopy. So remember, to do the diagonal homotopy, we had A and B and C in, and we wanted their intersection, and we moved it to computing this instead, up in Cn cross Cn. Okay? The new idea is that we can do basically the same thing, but we just replace the diagonal v of x minus y with this v of f that we want to intersect with. And it's even possible for f to bring in new variables, which is often quite an interesting thing to do. And I'll just mention that this kind of problem, if I want to say, suppose I have set A and I want to test if x naught is in A. One way to do that is to intersect A with just this variety. And if that's non-empty, then it means that x naught is in the variety. And it turns out that if you do our new procedure posing this problem to it, what comes out is something that we were already doing called the homotopy membership test. So it's kind of nice that everything ties together. So how does the new procedure work? Step one is to use the witness sets for A and B to get a witness set for A cross B in Cn. And that's basically you're moving from linears in the two Cn's to linears on the C2n. So it's just a simple process of moving coefficients of linear equations around. Once you have this linear equations, you can regenerate a randomization of f equation by equation. What do I mean by a randomization? If you have more equations than the codimension that you're cutting out, if you take a random combination of the polynomials, you'll preserve that set, and so you can compute on that instead. Then once you have regenerated f, you'll have witness points, and again we have to use isosingular deflation to get our witness system. And then an optional fourth step would be decomposing this into its irreducible components, which I haven't told you how we do, but I'm not going to tell you today. If you want to ask me, we can talk about that. I want to move on now and talk a little bit about computing real algebraic sets. And like I said before, there's another talk on this today, so I'm going to give you just the 10,000-foot view, as they like to say in industry. And let's start by talking about projections and cell decomposition. So let A be an irreducible algebraic set of dimension d and multiplicity 1. That's where I'm going to start from. If I have some set A with multiplicity greater than 1, I can reduce to this by replacing A by what I just write as iso of A. This is the isosingular deflation of A. It's actually, this procedure is not the nicest one, so it is kind of a limiting factor in what you can do practically. I want to make that clear, but in principle it can always be done with enough computation. So we can say that A is multiplicity 1, and let this be the witness set for A. And now let's assume that FA is real, meaning that it maps real points to real points. So the coefficients of the polynomials are real. And we want to find A intersect the reals. So we have this witness set on complex space, and we'd like to know something about the real points in there. So let pi be a linear projection from Cn to Cd. Remember, D is the dimension of A. Okay? For a Zariski open subset of CD, the A intersect the fiber over X consists of degree A isolated non-singular points. Okay? This still holds if my projection is a real one. So I have some projection onto real RD above a point in there. I get some number of intersections. Over the complexes, there'll still be degree A of them. But over the reals, some less than or equal to degree A of them will be real. Okay? And now let's define the critical set of A with respect to pi as this thing. I'm going to call it K. The critical set with respect to pi of A is A intersect the variety of the determinant here. This is our function, FA, our set of polynomials. This is the Jacobian of the projection. The determinant equal to 0 means it's singular. And I have A intersect that, and then we'll just consider the real part of that. So what is special about this? This is a necessary condition for the real root count to change. Okay? It means that two roots have come together, or a set is ending in a singular curve, or something like that. Okay? So being singular is a condition for the number of real roots to change. So if I'm down here, and here's the critical set. If I have some open subset that doesn't touch the critical set, then above the points in here, I have these nice sheets. I've got the implicit function theorem that I've defined nice patches above it. Some number of them are real. And now I can move around in U, and I can, by continuation, compute other points on these sheets. And I'd like to just put it together. So to describe the real points in A, it suffices to decompose RD, take out the critical set into cells, and use continuation to determine two things: how the real patches meet each other and how the real patches meet the critical set. Okay? And then I put a note here. Some parts of the critical set might have no patches meeting them. And an example of that, if you're familiar with the so-called Whitney umbrella, it's this nice surface, and then coming out of it is a singular line. So you wouldn't have any of the surface patches meeting this singular line, but yet it's part of the real set of solutions. So these kind of things, just like the Whitney umbrella, if nothing is meeting it, it's a lower dimensional singular set. And we can find those as well because they'll be part of K. So here's a illustration of that. Suppose this is my curve, and I've picked a projection. It's a curve, so I'm projecting it on R1. And where the projection is basically tangent, those will be critical points. Where the curve crosses itself, that's also going to be a singularity. I'll get a critical point there. In between the critical points, there's just nice arcs. And if I cut the curve in the middle, I'll get some set of points. And then I can, by continuation, go to the critical points each direction and see how the arcs meet up. See how they meet at the singular points at the critical set as well. And once you have all of that, you have a nice picture of the whole real curve. If you have a surface, it's a little dicier because now I'm projecting onto two coordinates. I get the critical set will be a critical curve. It's sort of the points upstairs that make the edges of the shadow downstairs. And then I have to carve up that two-dimensional set down there into cells. But you do that by also then decomposing the critical curve in the reals. And so you get critical points along that, and that's how you start carving up your cells downstairs. I'm going to let Daniel take you through more of that today. Let's just say then that to find a witness set for the critical set, we can use the intersection algorithm. So this is how some of this ties together. And one version, instead of putting the determinant to 0, I can say, well, let's take a tangent vector. I bring in a tangent space. Now I have A cross Pn intersected with this, and that is another way to describe the critical set. after you're done, you have to project away the tangent space, and you have the critical set. So we not only have to find the critical set, but then if K is higher dimensional, we then have to find a real cell decomposition of K, and it will also have its own critical set if it's high enough dimension, and you have to kind of go down. So if A is a curve, then like we saw in the previous illustration, K is just a set of points, and so the real points in K are the endpoints of the cell decomposition. If A is a surface, then the critical set's a curve, and we have to apply cell decomposition to that. So then we're going to be looking at the critical set of the critical set of something, and this is where the procedure starts to get nasty. But what we have at the current stage is a complete algorithm for the curve case and the surface case. And we have this Bertini real project that has code to do these things. And as I keep saying, I'm going to let Daniel show you some really nice pictures and describe this. But let's look now at applications. I think I'm doing okay on time. This first one I'd like to talk about is it's connected to, back to this classic thing from mechanics, the 4-bar linkage. If you take a 3-bar thing, you make a rigid triangle. We build bridges out of that. But then when you want things to move, you put in one more link, and now you've got a quadrilateral, and it can move. And it's surprising what mechanical engineers can do by manipulating these things to make various devices. So it's a classic thing because it's like a fundamental machine element. There's different things you can do with a 4-bar linkage, and here are some of the main ones. One thing you might do is what we call body guidance. So body guidance says, I've got some link that I want to move to several different positions. And I care not just about, when I say, let's say poses, I care not just about position, but also orientation at each of these. So, for example, it could be the suspension of a car. And I care not, I got to allow the tire to bounce as you go over potholes, but I also care about its orientation as it bounces. You don't want it to wobble. So, in fact, it's a subtle thing, but exactly how the orientation changes as it bounces has an influence on how stable the vehicle rolls. So it's kind of a critical thing. You could also be opening the trunk of your car, and that's a link that moves in space, and you may specify a certain kind of path you'd like that to take. And you design a linkage to do that. If you look in the trunks of your cars, you will find a mechanism there. Some of them have a simple hinge, but a lot of them have a 4-bar linkage, or even a 6-bar sometimes. So body guidance. You specify poses, position and orientation for the coupler frame to attain. And there's a classic Burmester problem. This is why we're calling these Burmester. A guy back in 1888 came up with solutions for when you give the maximum number of poses. On the other end of the spectrum is what we call path generation. That's like what I was saying over here, where I just give points that I want that coupler point to go through, and I don't care what orientation it has when it goes through it. So that's called path generation, and we ignore orientation, and the maximum number of points you can give and still expect a solution is 9. And so Alt put forward the 9-point problem in 1923. The newest thing that we started doing just a little bit ago with the guys at University of Dayton is what we call mixed Burmester, where you specify some poses and some positions. So you care about orientation for some of the things, and then you just want to kind of return any way possible through some other positions. And you don't care about the orientation on the rest. Some terminology. This is the coupler point, the coupler frame. This we call the circle point, because when the linkage moves, it moves on a circle. We call this a center point, because that point stays fixed there, okay? what is the whole mixed Burmester family of problems? You can give up to 9 points and up to 5 poses. You don't see 9 points on here because if you give only points, you can specify an orientation at one of them for free. So the 9-point problem in this chart is really the 1 pose 8-point problem. So it sits here. And this is the dimension of the set you expect for general data. So if I give you general 8 points and 1 pose, I expect a 0-dimensional solution set. If I only gave you 7 points here instead, you expect a curve of solutions, and so on up the scale. And Burmester worked these 2 problems, where you give the maximum number of poses, or just 4, and you expect to have. It's interesting. The problem decomposes. Let me go back. If you give all poses, you can look at the 2 sides independently because they're only kind of coupled together through the orientation part. And so that's what makes these problems easy. This is a 2-dimensional set, but it's really a 1-dimensional set across itself. You can solve for the curve, and you've got it. So that's what Burmester did. And up here is Alt's problem. It's posed in 23, first solved by continuation in 1992 by Wampler and those guys. Here's the chart. And these numbers in here, I'll give credit to John. He generated all of these, looking at the dimension, at the degree of the solution set in each of these cases. So here's the result from 1992. There's 8652 solutions here. Turns out when you give all points, there's an order 6 symmetry group goes on. So there's like 1442, this divided by 6 really distinct solutions, taking out the symmetries. That symmetry doesn't apply anywhere else in the diagram. So we list the 8652, not the 1442 here for comparison. An interesting one that we looked at a little more, you give 3 points and 3 poses. This is a curve of degree 362. And here's a picture of it. So I'll just point out one thing. If I want to do this curve, the one way to sample this curve is to take the 3rd point and turn it into a pose. So move to the 2, 4 space by giving an orientation at that 3rd point. And then try a bunch of different orientations. At each one, I'll have 60 solutions. And then you can plot those. So then you get a picture like this, where the points you don't know how they connect to each other. You've sampled essentially this curve by that means. And this is what the guys first did down at University of Dayton. We take our real decomposition approach to this, and we can turn that picture into this picture where we really do have all of the arcs. We know exactly where anything ends and turns and how it all fits together. So it's kind of cool. It's not that easy to do a degree 362 curve. If you don't believe me, I encourage you to try it yourself. Here's another one, and Daniel did this one. It's another 3-3 Burmester curve. If you zoom way out, you see the asymptotes that go off to infinity. You could compute those directly by intersecting the curve with a plane at infinity, and you'd see where you expect these to go to. But there's something interesting going on down in here. So let's zoom in, and it's looking kind of naughty. And let's zoom in again, and it's looking pretty interesting. And one thing that you see in this plot, and this, by the way, is the projection onto the center point. I believe it's a center point, not the circle point. And so these are all the designs that meet the specification, and this is in the plane. Where can this point be? And it can be at any of these points, and you pick one of these, and the rest of the mechanism is determined. And it's interesting. There's something going on here, here, and here. And if you plot that as a triangle, it turns out this is what we call the pole triangle for the three poses. And what's a pole triangle? If I give you two poses, then on the perpendicular bisector of these, if I put a link here, I can take this point to this point, right? By rotating. And somewhere along here, if this is the angle of rotation, somewhere along here, the angle between these is also theta. So it not only takes that point to that point, but it takes this frame to this frame. That's the pole of the two frames. We had 3 frames in the specification, so there's 3 poles, and this is where those poles are. So that was an unexpected result, that if you project this high degree thing onto the circle point coordinates, that these poles would show up. And even more interesting, I said, well, Daniel, tell me where these points are. He said, well, upstairs where I'm doing the computation, nothing crosses. It's only in the projection that they cross. So it's kind of a surprising thing. And the mechanical engineers at Dayton said they were the ones that figured out what this triangle really means. Okay, and then for the rest of the time, we're going to talk about sphere packings, if nobody has any questions. So let's look at this sphere packing problem, and again at this table of new seeds. What is the problem? Determine all rigid packings of n or fewer identical spheres. And why is it interesting? This models how spheres immersed in a liquid form into colloidal mixtures of particle clusters. So if we model this as hard spheres with short range attraction, then they're basically going to stick to each other, and the centers will be at the distance of twice the radius, or the diameter of the spheres. So if we know a complete list of the packings, we can determine the energies of each packing and then predict cluster distribution. So if you put the n spheres in solution and wait for them to come to a cluster, they'll distribute according to the energies of the various clusters. And as I mentioned earlier, Vinny Manoharan at Harvard actually runs experiments, so you can go back from the math predictions and see if it's predicting what the physics experiment actually shows. And one of the interesting things is that this opens the possibility of designing colloids, or for micro manufacturing of desired clusters by mixing spheres with different DNA coatings. So if you make it so that not all the spheres are identical, but they stick to each other preferentially in certain patterns, you can try to make a system where you just put the spheres in solution, you wait for them to come together, and they'll be in the shape that you wanted. So let's take on this problem of determining all packings of size less than or equal to n. So one of the steps is to enumerate all non-isomorphic, minimally rigid adjacency matrices A. What is a adjacency matrix? It's one that has a sub ij is 1 if sphere I touches sphere j, and it's 0 otherwise. It's just one way of encoding what is the set of contacts. Non-isomorphic means you can renumber the spheres and get a different AI that means the same thing. So we don't want to redo that problem. We want to find just the non-isomorphic ones. And then what does minimally rigid mean? It means it has exactly 3n minus 6 contacts for n spheres. Where does that come from? Well, each sphere has 3 coordinates. And then if we've constrained it by this many, I'll have 6 degrees of freedom left, which is the degrees of freedom of a rigid body. It can translate with 3 degrees of freedom, rotate with 3 degrees of freedom. So if you have 3n minus 6 contacts, you're in this what we call minimally rigid situation. And so you can start enumerating under these conditions, but you can also prune by certain impossibility rules. So if I have 2 spheres in contact, and I ask the question, how many spheres can I put in here that are contacting both of them? Then you can fit at most 5 in there. So that's an example of a limit. So a adjacency matrix that had 6 spheres in contact with both A and B that contact each other, is impossible. You don't have to consider that. There's a couple other rules of that sort that can help prune the problem down. Okay, let's say you can do that and you can enumerate those. That's a problem in graph theory. For each one of the A's that's left over, we have to solve a system of distance equation. We want to find all the isolated real roots, and it's not necessarily a unique answer. And not all of the answers are of interest. So here's an example. Suppose I have this set of it's easier to look at the spheres shrunk down and then draw a link of the ones that are contacting, so you can see through the figure and see what's contacting what. So each one of these represents a sphere. In the real thing, you would grow these till they touch, right? So this is a good packing because all of the contacts that are specified are satisfied, and no sphere that's not contacting is closer than the diameter distance. Here, this arrangement, it satisfies all the specified distances, but you can see that some of them are too close. So if I started expanding these spheres to their true size, these spheres are interfering with each other. So you find all the isolated real solutions. You call out any that have interpenetrating spheres. And then an interesting thing to do is detect what they call chiral pairs. Basically, if you take the mirror image, all the distances are preserved. The mirror image could be the thing back again, or it could be a chiral pair where the mirror image is different than the original one. So, if you're going to do all of that, it's a pretty big program to try to solve all of them. And one of the interesting things is that you don't need to solve every packing from scratch. You can decompose them into a series of previously solved subproblems, and we call these packing rules. So each of the subproblems is a parameterized polynomial system. And after solving a rule for generic parameters, subsequent appearances of the rule can be solved via parameter continuation. This will become a little more clear in another slide. So the packing rules can be represented by a kinematic type graph. And what I'm going to show you next is some of these. So here's my notation. There's 2 types of nodes in these graphs. One is P for a point, or R for a rigid body. So a rigid body stands for some collection of spheres that are rigid with respect to each other. They have enough contacts that they become a rigid body. And then I have 3 types of edges in my graph.
Oh, Charles, Jonathan has a question. 2 minutes.
2 minutes? Ah, okay. Somehow I was hitting a different target. Okay. We have simple contacts. We can share a sphere between 2 rigid bodies, or we can share a pair of them, so we have like an edge. And this gives you this minimally rigid rules. And here is the chart from the original one by Arcus, where they have, here's how many adjacency matrices, how many non-isomorphic ones they are. It's not nearly as bad as this, but it's still pretty bad. But then the minimally rigid ones grows a little slower. And then the iterative ones is most of those. And by iterative, she means that you can get it by just 2 rules, a tetrahedron rule, which I'll describe in a second, or just gluing 2 rigid bodies together on a triangle. And this is the leftover ones, what she called non-iterative. You can see it's starting to grow at n equals 10, and it's going to grow much faster after that. So here's the kind of rules. The tetrahedron rule is I have a point with 3 contacts, so that point's position will be determined either here or mirror image below. So it has 2 roots, but we have other ways. For example, if I take 2 rigid bodies with 6 contacts between them, Those who have heard some of my previous talks, that's equivalent to what we do in kinematics called a Stewart-Goff platform, where there's 2 platforms and 6 legs. It has at most 40 roots, and there's various other examples. So each rule gives one or more solutions, and then that would be a rigid body that you can build bigger things out of. And the vast majority of big in-packings have at least one rigid sub-packing, and so you work your rules up that way. So let's wrap up. Numerical algebraic geometry point out that witness sets are the fundamental construct. Irreducible decomposition is key, even though I didn't tell you how to do it today. And software is Bertini, an open source free thing. Intersection algorithms, we're able to do further investigation on sets represented by witness sets. Regeneration is one of our most effective approaches in this. And we need this thing called isosingular theory to complete some of the singular cases. And then when we do cell decomposition of real algebraic sets, it's a way of building a complete map of the real set, how everything connects together, uses intersection and isosingular deflation, and limited at present to curves and surfaces. And I've talked about a couple of application areas of robot mechanisms and sphere packing. So let's call it done. Is there any questions?
Any questions? Yes.
Does your robot have some kind of learning algorithm so it knows how to move?
You mean Robonaut?
Yeah.
Well, yeah. It can be operated several ways. It has autonomous modes. There's cameras in the head. That's why it has a head, so there's a vision system. They have routines for doing some of these things, like finding a button and pushing it, that's completely autonomous. It has another mode where a person can look through the eyes of it and control it remotely. The learning aspect, there is a little start on that. I'd say it's not very far yet. There's a lot of learning going on the people involved.
Yes.
When you solve this matrix adjacency,
Uh-huh.
do you find a lot of complex roots
Yeah.
in addition to the real roots?
Yes. Yeah, definitely. So, there's a whole other class of algorithms, which if you want to work just on the reals, you can do these exclusion box cutting methods. That's another way to come at these problems. We're coming from this angle, but that's another way you can go. When it gets high dimensional, the cutting routine, there's a lot of dimensions to cut in. So it's not clear. If there are no real solutions, often the exclusion method can conclude that pretty quickly. If there are, though, then it might work a long time to find them. So these are some of the things. It might be that checking quickly, are there any, to some resolution before you go do the homotopy. You could put things together that way.
Pascal?
Yeah, I have a question about the witness sets. So you use those to find components of positive dimension.
Yes.
Can you also handle the case when there are components of various dimensions?
Yes. Yeah, basically the way the algorithms work is they test at every possible dimension. And so you cut with something of codimension 1 and you see if anything is there. Then you cut with codimension 2 and see if anything's there, and so on. Work your way down the possibilities. And at each level, you're looking for isolated roots that you've sliced out there, so you're in business. There actually are these cascade methods that use the result at one dimension to feed the next dimension, so they can be a little more efficient than just starting over from scratch at each dimension.
Frank?
Yeah, well, your Bertini reals seem to have some of the functionality of other approaches to this problem, like cylindrical algebraic decomposition.
Yeah, it's
or symbolic numeric methods. I think like Mohawk or other collaborators have worked on that. I think
Yeah.
so. I mean, is any comment on that? I mean, you were talking about how your performance and how is it compared to these other methods?
I would say it's a maturing technology. I think we're getting to the point where it might be worthwhile to do some runoffs to see, up to this point, we've been making sure our algorithms are correct and running reasonably efficient. No reason to do a runoff until you're kind of at that stage. So I don't have an answer now on how they compare. They're obviously, the cylindric algebraic decomposition is quite closely related to this, but though in concept, but in the details of what you compute, they're quite different.
Just the question is, because I was wondering if you're aware of all that other work.
Oh yeah, yeah, I'm aware of it. Another problem with doing comparison is that somebody has to get to be an expert in the other thing so they can run it, and until the software gets to a level where idiots can run both and then see how they come out, it's hard to compare.
Yes, Mike.
What do you do in one of these cases where you've got exponentially many isolated real roots all degenerate?
I work really hard. Yeah, there's no good answer to that.
So, related question is, what sort of guarantee does Bertini give about approximate correctness of the answers that it does produce? So in particular, I can easily code up integer linear, 0-1 integer linear programming in polynomial system solving. So if I do that, in other words, if I encode a hard combinatorial problem inside Bertini, does it give me bogus answers? Because then that's not, it'll be more helpful if it says, oh sorry, I don't know, as opposed to giving bogus answers, which would be, then somebody has to go and...
Well, how to answer that? We do use floating point. There is the possibility that when you track a path, you could cross paths or something. We make our algorithms highly reliable. We have ways of testing, are we carrying enough digits and so on, but it's not a perfect guarantee. There is stuff out there for guaranteeing that you have taken small enough steps that you don't cross any paths. Unfortunately, this is the alpha theory. This can be used for that, for example. Unfortunately, it's too expensive to carry it out that way, so we take a more practical route. You can, if you have a non-singular isolated route that you have an approximation to, you can use the alpha theory to certify that really is near an actual root. Unfortunately, if it's a singular root, there's not a good method for that I know of.
Other questions? All right, let's thank Charles.